Okay, so to finish off what we were talking about this morning, so that's just a recap of the Strybeck curve, and the debate is how do we end up with a structure like articular cartilage that has such good properties, yet in reality fits about here on this plot of bearings when we consider its viscosity, velocity, and contact load. And we touched on too the shear thinning of synovial fluid, so as its shear rate increases, the viscosity gets thinner. We know that articular cartilage is elastic, it deforms, it has shock absorbing properties and benefits because of that, but it also expands the contact area too. One of the benefits of cartilage being deformable is that it can absorb fluid into it, and then as it's compressed, the compressive force that deforms the tissue squeezes synovial fluid back out again. So much like a bathroom sponge. And so we know that lubrication decreases friction. We understand that from the kind of basic scientific principles. It also reduces mechanical wear. If there is less contact between the surfaces, and to the extent where there is no contact between the surfaces, then it's reasonable to assume that there's not as much debris generated when the two slide past one another. And this is a closer look at what we've seen on the board earlier on. And these are types of lubrication mechanisms that have been proposed. And we'll look at these tomorrow in more detail. But as we consider the right-hand edge of the Strybeck plot, we're in this lubrication regime where the two surfaces are separated. We describe that as having a film of fluid, a film of lubricant between the two that keeps the two apart. And then through the years, people have come up with potential justifications as to how a fluid film might exist, knowing the characteristics of the synovial fluid and the articular cartilage. And so we'll discuss those in more detail tomorrow, but that's to say at this stage, is it because the synovial fluid has molecules within it that stick to the cartilage like we discussed this morning, and you get some kind of highly efficient boundary lubrication, which is to the right-hand edge of the graph? Or is it because there's a clever combination of the size and the dimensions and the deformity of the articular cartilage, and then the synovial fluid that is within this fluid-tight membrane that allows some of this kind of pumping type regimes to be realized? But we'll discuss these in more detail tomorrow, and we'll also discuss tying it back into our gait cycle. So that is our ability to walk, and where we have our right leg and our left leg in the swing phase, or the heel strike, the stance, or the toe off. They're the four main features of the gait cycle. And we have relative joint loadings through those times. Then it's proposed that you can have a number of those previously mentioned regimes fit to the gait cycle to come up with a narrative, a story that in some way justifies how the joint can be as effective as it is. But we'll touch on these in a little more detail tomorrow when we look at the lower limb in particular. But one of the other key parts of the musculoskeletal system are the tendons and the ligaments. And whilst we group them together here because biomechanically their structures are quite similar, we need to be aware that anatomically their functions are very different. Ligaments tie bone and bone together. So they typically span the knee joint or the hip joint like we saw with the medial, lateral, collateral ligaments in the knee on the inside and outside, and the anterior and posterior cruciate ligaments that cross over in the center. So they are our ligaments that link bone to bone. Tendons link muscle to bone. So if we didn't have our tendons, then we'd have a stable structure that wouldn't be able to move, because it's the muscle contraction tied into the bone via the tendons that enable our body to move. And so biomechanically, they're very similar. Their mechanisms of tying into neighboring structures are very similar, but anatomically, they're fundamentally different. So tendons link muscle to bone, and they transfer the contractile force generated by the muscle to enable skeletal movement. If you didn't have a method of transferring that contractile force to the skeleton, then effectively you wouldn't move and you'd have muscles that were shrinking and achieving nothing. And ligaments then create the stability in the skeleton by linking bone to bone. They both act as very stiff springs. So they have a strain of about 6%, and then they rupture. So they're very stiff, but they're also very strong as well. There are benefits to this. It enables a storage of energy. And so energy that's generated in the muscles is effectively stored in the tendons and transferred onto the bone itself. And so that means that you can effectively have an enhanced ability to jump because you have a spring that's extended that recoils then as you begin to move. And we can drill down into what a tendon or a ligament looks like. So we have the bundle of tendon that's wrapped up in an endotenon. Within a bundle are several fibers. Within a fiber is a fibril, in a fibril a microfibril, and then finally a molecule of collagen. All of these are collagen. So they're very tough materials that can be extended only to 5, maybe 6% strain, 10% in some studies depending on a variety of conditions, but they have less than 10% strain, and that's beneficial. If it was a huge amount of strain if you're allowed to extend these things over a great distance, then the contractile force generated in your muscles would be ineffective at being transferred to the bone because the rope that's connecting the two would continue to extend. It would be like trying to move something with an elastic band. You would continually stretch the elastic band, you would continue to apply force, but no movement would happen. So these are very stiff, but also very strong. They don't remodel well. So unlike bone, they don't remodel very well. They're not very easy to repair. But they do have a limited ability to adapt to the environment that they're in. And so the thicker a tendon is, the greater the amount of strength that it will have. And so ordinarily, where you have strong muscles, you would have strong tendons. The obvious example being in your calf, and you can feel the size of your calf muscle, and you can follow that down and feel the tendon itself. And you can actually dig behind the tendon to get an appreciation of the cross-section of the tendon. The Achilles tendon is the biggest muscle in the body, and it has a number of distinct geometries to it. It starts out very flat, and then it twists through 90 degrees until it becomes a circular cross-section in the middle, and then flattens again as it inserts onto the back of the foot. And indeed, this is a cross-section of the Achilles tendon. So to provide some orientation, this is your heel bone, and your toes will be out here somewhere. Obviously, our head is some distance up here. And it's this shiny white structure that's our Achilles tendon. And so if you were to grab the back of yours, you would probably see the cross-sectional area here is maybe 7 or 8 mil in terms of thickness. So it's still relatively thin, but is very strong for that diameter. We had a question yesterday about this part here. How does the tendon and the bone interact and interface with one another? We'll come on to use this picture shortly to describe that. But tendons are very flexible, but that flexibility can cause problems. As you put your toes downwards in plantar flexion, you'll find that there's a lack of tension on this. So if you're sat on your chair now and you were to bend your toes downwards, you'd feel that this is actually quite wobbly. And there's a risk of this actually folding into this cavity and creating a fold or a bend in the tendon. And so you have a lump of fat here which effectively serves as a space filler to avoid that buckling from happening. The fat doesn't have a huge amount of functional use apart from that, but it stops the tendon from bending when it's particularly slack and there is excess length. Whenever you do a dynamic activity, then it will be under tension because the calf muscles will be contracting. But we can zoom in more detail, and we start to get an understanding and an appreciation of quite how the tendon and muscle, the tendon and bone connect so cleverly together. So we identify here, this outline here is the outline of the bone. Here we see our trabeculae. Not a lot of cortical bone, very thin. And the rest of the bone extends off to the left. And the issue that we were describing yesterday is that this tendon is, as we know, very flexible. And we'd have the circumstance where we have a very rigid bone and a very flexible tendon that are interfacing with one another. And a good example is here, actually, whereby we have a similar situation. We have our rigid box and our flexible cable. And the engineers have designed this rubber grommet so that when we load it, we see that there's only a gentle curve at that interface. And so the risk of a stress concentration happening at the interface between the two is mitigated. And so the risk of premature failure of the tendon is mitigated against as well. The human body does that in a very sophisticated way. This body of green tissue here is still the Achilles tendon, but it's actually a staining protocol under a microscope that's enabled the different mechanical properties of these tendons to be highlighted. And so in essence, the green area is a stiffer part of tendon that is exposed to compression. And so it's known that this area is under compression, and so the tension or the stiffness of this part of tissue is increased relative to the parts more proximal. And so we have a relatively unstiff tendon, a relatively stiff tendon, and then a very stiff bone, which is very similar to our relatively unstiff cable, our relatively stiff grommet, and then our very stiff box. And so that interface, and also the fact that if we were to zoom in closer, we can see red parts projecting into the green parts of the tendon, means that we're not talking about a simple interface that one has been effectively glued onto the other. They're actually interlocking. And so the contact area between the two different tissues has been expanded, and so the strength is greater still. We find that when we get tendon ruptures, normally happens about here. 5 centimeters above the point of insertion is the most common point of tendon rupture. Happens in about 95% of all tendon ruptures. An avulsion fracture, where the tendon is pulled away from the bone, is a cause of about 5%. Avulsion fractures tend to be repaired by screwing the tendon back onto the bone. Ruptures tend to be repaired by suturing. An Achilles tendon rupture in sport is, again, not dissimilar to a cruciate ligament. You're looking at 9 months to a year, a full rupture, 9 months to a year out of the game. And that's because tendons are very slow at remodeling. Unlike bone, where within 6 weeks you can be back playing again, and okay, the repair process takes up to a year. Here you can't really do anything physically exertive until that point. One of the challenges comes because inevitably this tendon will curve. As the feet point upwards, the tendon has to change shape. When the feet point downwards again, they change shape. Now, one issue was if this was a single structure, you would have a stress on the inside, a compressive stress on the inside, and a tensile stress on the outside. And so we consider again these fibers. And one of the benefits of these fibers, so having individual strands of rope within a whole rope, is that as we get a curve geometry of a tendon, these different collagen fibers can slide past one another. So the fibrils and the fibers can slide past one another because of the construction of the tendon. So each fascicle is surrounded by an endotenon, and that contains both nerves and blood vessels to supply the tendon. But that structure allows minimum friction as the tendon does curve, and it curves all over the body, in the wrist and the hand and the ankles and so on. It curves and it allows the inner part of the tendon to slide relative to middle, to slide relative to the outer side. And indeed, if we were to consider the outside edge of the ankle, this is a bony prominence. So you can feel this tendon on the outside edge of your ankle. It comes down from the muscle, then turns at a 90-degree angle. So we've suddenly got this issue where we have multiple structures within the tendon that have the ability to slide past one another. We also have an area of stiffened tendon. So much like the area that interfaces with the bone is stiffer to give it a mechanical advantage, this area becomes stiffer because it's continually rubbing past this bony pulley. So this is what it says on the tin. It's a pulley made out of bone. So it serves solely to redirect the tendon. Now, the reason it needs to redirect the tendon is because this attaches to bones within the foot. And in order for you to get enough strength for your foot to be functionally beneficial, you need a large muscle. And so the cross-section of a muscle is proportional to the amount of force it can generate through contraction. We need a lot of force in our foot because that's ultimately stabilizing the rest of our body. So we need a lot of force in our foot, which means we need a big muscle. But we haven't got space in the foot for large muscles. There's no space. By the time we take the bones out, we can't have big muscle bellies. So the muscle is located in the lower leg. The bones that we want to pull are located in the distant foot. And so we need to have this tendon that links the two together that inevitably has to go via 90 degrees. And it's this bony pulley that allows that to happen. But rubbing anything past a pulley for 70, 80, 90 years is going to cause some kind of wear. And so again, the tendon has remodeled, become stiffer to minimize the risk of that wear happening. In the wrist, it's common to get tendon inflammation. Secretaries, in particular, when they use keyboards for a lot of time, have the risk of tendon inflammation and surrounding tissues that become inflamed as a consequence of overuse. Overuse injuries and tendons are one of the big risks. And so some parts of the body have, over time, evolved to accommodate that risk. Other tendons haven't evolved in such a way because the risks and the loads that they're put under are very new. And so if you consider the type of work that secretaries do, sat in front of a computer for a lot of time, the function of the tendons in the wrist is very new. And so the body hasn't had time to evolve to have fibrosis around those bony areas and those bony pulleys. Maybe in 50, 60 years' time, when we start to look back at how different the body's looking, it may have changed and there may be tendons in the wrist and the hand that also demonstrate this reinforcement as a consequence of our changing lifestyle, our continual reliance on computers. But at the minute, this is a good example of a change in the mechanical properties of the tendon as a consequence of the environment, the biomechanical environment that they are operating in. The retinaculum of a tendon is something that's often overlooked, and that's to say that if we consider the tendons attached to the end of our fingers, the tendons attach to the end of our fingers, but the muscle belly is actually in the forearm. And so logic would say if your muscle contracted in the forearm and the ropes, the tendons from those muscles actually are attached at the other end to the fingers, then why aren't these tendons taking the shortest possible route between the two? And that is that you would effectively have a hand that looks almost like an American football glove or something similar. You would have tendons that would go the most direct route over the palm of your hand. And it's because of retinaculum that doesn't happen. So your tendons are tied on to your fingers. They're tied on to the bones in your hand to avoid them taking the shortest possible route between your forearm and your fingertips. But again, you're constraining the movement of the tendon. You're giving it more things to rub past and slide through. So we see that there's an elaborate tendon sheath that covers the tendon. The tendon sheath will be heavily lubricated to ensure that whenever you move your fingers, this tendon can slide as seamlessly and as friction-free as possible through those tunnels. Those tunnels are there to tie them down to the bone as much as they can. So they're exerting a compressive force. And so it's ultra important that that force is in some way mitigated to avoid the tendon surface being roughened up. And so this tendon sheath and the surrounding fluids are very important in minimizing tendon friction. Where that fails, you end up with things like carpal tunnel syndrome, which is a condition that affects the wrist. Tendons are yet another material that have viscoelastic traits, and that is that if you hold the tendon at a fixed length in a machine, so you would load it to a certain length, you would walk away from the machine, and you would come back, and the reading on the machine, the load on the machine would be lower. If you had a piece of rope and put it in the machine, walked away, came back in 10 minutes' time, you would be confident that the machine load would remain unchanged. So the load cell wouldn't have in any way had a reduction in load exposed to it. The strange thing about tendons in particular, because you can draw an analogy with a rope, is that you apply a load, you walk away, you come back, and that load is reduced. Nothing's changed on the machine. The crosshead is still in exactly the same place. But your rope seems in some way to have changed such that there is less loads being exposed onto the load cell. Similarly, if we apply a load to our tendon and a load to our rope, if we were to do that at the same time and walk away, you would expect fully that you come back and the rope is the same length. However, with our tendon, you would walk away, you would come back over a period of time, and it would actually become longer. So the tendon increases in length with time, and depending on the amount of load, that will change. Take the load off, and it will gradually go back into its original length. So we can see that a tendon has a fairly or a relatively low stiffness at the start. If we look at a tendon microstructure, we can see that there are obvious waves in the fibers that make up the tendon. So that's a relaxed piece of tendon. And we've got a fairly chaotic, relative to other biological tissues, a relatively chaotic arrangement of those fibers and fibrils of the tendon. And needless to say, intuitively, you could stretch that quite easily without requiring much load. You could get it until those fibers are straight. And so here, we can get some extension, some elongation, whilst applying relatively little load. That's because in the first instance, we're taking out these curves and we're straightening them, and that's quite easy to do. Once they are straight, however, in a circumstance such as this, increasing the length of the tendon becomes harder. Harder physically in terms of the load that you have to apply. Because there's no obvious slack left in the material, in the tissue. And so you can continue, of course, with a machine to extend it. And visually you don't know the machine is working harder, but it is. Because there's no slack left in the tendon, so it has to apply greater load to get the same amount of extension. So if we're looking at our plot here, about a third of the elongation takes you to about a tenth of the load. Our second third takes you to about 60% of the load. So there's a marked difference when you get those fibers straight. At that point, the tendon becomes a lot stiffer. And it keeps becoming stiffer until the load that you're exposing these fibers to becomes too much. They don't fail together, but there's a partial tendon rupture. You get some of the fibers failing. When that happens, of course, the load drops off instantaneously and then goes back up again, and you get more and more failures until ultimately there's not enough cross-sectional area left of the tendon and it all fails. And this is a typical graph of any tendon in the body. The extent of elongation, the extent of load depend on where it's from. But in terms of the strength of a tendon, then it's pretty strong. 20 to 35 megapascals versus other biological tissues. Cancellous bone is very strong as well, but the Young's modulus 2 is pretty stiff. Elongation is about the same as stainless steel. So you may have done those first year labs where you have to extend a piece of stainless steel until it snaps. You don't think stainless steel is particularly easy to elongate, and indeed the amount of elongation that you get in a tendon is not dissimilar. So they're very stiff materials. In terms of strength, then you can do all kinds of activity with a tendon before it fails. You can climb and jump and run, and then it, for some reason, is the most innocuous of all activities that typically cause the tendon to rupture. In soccer, for example, one of the more common occurrences is you can see a player running along almost at times off camera because it's such an innocuous event, and they'll suddenly stop running and turn around. And the theory is, or certainly the story goes, that when your Achilles tendon ruptures, it feels as though you've been shot from behind. That's the level of pain that you're dealing with. And the reaction to turn around is to effectively see who has shot you. But there could be no one around. So you're not in a particularly high portion of this curve. You could be jogging along, and then suddenly, for a reason that remains unknown, you turn around, you writhe around on the floor in pain, and then later on at the emergency ward, you get diagnosed with a tendon rupture. And so they're very strong tendons that rarely fail, yet when they do, there's not really a biomechanical consequence or an understanding as to why that happens. You could nail a small car to the ceiling using a tendon, the Achilles tendon. They're that strong, and so their strength is not to be in any way underestimated. And if we go back to this image here, one of the things that we need also to be aware of is the damage that a tendon can do. Whilst they're not particularly easy to extend, they're quite stiff. When we move our toes upwards, this angle between the two decreases. And the space between the two is very much dependent on your own personal anatomy. So this bone here could be far more prominent than is in this picture. It could be far less prominent than is in the picture. And so whilst you could reasonably expect to get 40, 45, maybe even 60 degrees dorsiflexion, so your toes come upwards, in some instances, that may mean that there is no gap there at all, i.e. that the tendon and the bone are against one another. Now we understand that the tendon has an ability to strain, although not by a huge amount. If you can imagine yourself in a sprinting start type position, your tendon and bone would most definitely be in contact. And then there's the opportunity for the tendon extension to actually rub against this bone. So you'd have potentially abrasion of the tendon against the bone. And this is, particularly in athletes and long-distance runners, quite a common occurrence. You end up with the tendon and the bone rubbing against one another, because the tendon is not just rolling against the surface. Because it can extend, it's actually abrading slightly against the bone it contacts with. We see in some instances the bony prominence that the bone runs over. So we see this bony prominence here develop an additional layer of cartilage on the top. And indeed, the tendon develop a layer of cartilage on its surface as well. So where you have contact between the two, so where that space becomes too small, particularly in elite athletes that have overuse injuries or are at greater risk of overuse injuries anyway, you can end up with there being micro fretting. So the principle of it being that the strain is relatively small in terms of magnitude, fretting being that it's rubbing against the surface continually. So you have micro fretting of the tendon against the bone, particularly when the toes are rotated upwards. The body can, to some extent, mitigate against this risk because it can develop reinforcement of this tendon and bone surface. And so we have the development of tissues called fibrocartilages. So the tendon and bone can become fibrocartilaginous. They become stiffer. And they also generate enhanced tribological characteristics. They are better at allowing surfaces to slide past one another. So not only do we see this increase in stiffness localized to the tendon insertion, but in some instances, and in particular, where this bony prominence is greater in size, meaning that the contact between the bone and the tendon becomes more frequent, then we can see an evolution that indicates the tendon is responding, albeit slowly, to the different mechanical stress that it's being exposed to. So tendons and ligaments as well, we need to consider the two together. Have a very disorganized structure when not loaded, but when loaded becomes straight, and that process is quite easy to do. If we were to leave the tendon extended, then over time the force required would be reduced. If we were to leave the same load on the tendon, then it would eventually lengthen. And this can continue up until a point where we get failure. And so we'll have some fibers that fail initially, and then ultimately the tendon or the ligament fail entirely. The results of tendon or ligament failure tend to be catastrophic. They're slow at remodeling, and so repairing them is a lengthy process. Any questions on tendons or ligaments?
The bone gets ruptured, but as per these numbers, the tendon will rupture, then fracture will occur, or there are some cases where only fracture, the bone will rupture.
Good question. What you tend to find is that fractures occur in the middle of the bone, because that's the part of the bone that's most vulnerable. But there aren't many tendons or ligaments near the middle of the bone, because the tendons and ligaments all operate towards the ends of the bones, where the joints are, whereas the most vulnerable part of the bone is, certainly with the longer bones, is the part in the middle. And so it's rare that you would get a tendon rupture and a bone break at the same time. Normally, the consequence of one will inadvertently protect the other. And so if you had a cartilage in a ligament in your knee rupturing, then the release in tension of that is caused by that ligament rupture is probably going to save the cartilage and the bone around it as well. If the ligament didn't rupture, then it may be that you end up with a catastrophic bone failure, which becomes even harder to repair. So it might be that the body is deliberately or maybe inadvertently protecting itself. And so it's probably far easier to repair a ruptured ligament at the knee than it is for the ligament and some bone to be pulled off the edge of the knee. And so perhaps the kind of failure mechanisms are in some way evolved to ensure that the least serious one happens, depending on the type of scenario that you're talking about. But it would be rare, and I can't think of an example off the top of my head where you would get bone fracture and ligament rupture at the same time, unless you're involved in a fairly high energy, maybe car, automobile kind of collision, where your body gets deformed and distorted very quickly. Perhaps in that scenario you can imagine that you would get bone fracture and ligament rupture at the same time, but that would require a relatively high energy impact, and not one that the body could necessarily resolve itself. So in a sporting environment, you would be incredibly unlucky to get a ligament damage and bone damage at the same time, because in sporting environments, whilst the injuries are serious, the energies aren't huge. If you go and stand in front of a truck going at 80 kilometers per hour, then clearly your range of injuries are going to be more serious and more extensive, and so the probability of you getting bone fracture and possibly in a totally different joint ligament rupture at the same time would be increased. But you would need to go to a kind of an extreme example such as that to find a situation where more than one serious injury happens at one time. Okay?
So the energy will be transferred through tendons only to the bone. So bones are having less Young's modulus and tensile strength. So in that case, I can say that it will be acting as a fuse, and bone will be acting as a supplementary appliances. The fuse will first.
Yeah, I think that's probably a good way of looking at it. That certainly in extreme circumstances where and so it would be difficult to find an activity that you could do yourself that would expose yourself to bone fracture or ligament rupture. I mean, I think the level of perceived risk would be such that you just wouldn't do it. But if you were outside walking across the road and someone hit you with a car, or you're out there playing football and someone came and tackled you in a fairly aggressive manner, then that would be a risk that you hadn't been able to avoid. And the energies there would be such that your ligaments, in effect, would act as a fuse. They would protect the joint by dissipating energy and rupturing, as opposed to remaining stiff and that energy in some way being dissipated through the joint surface. The one thing that we do know is that any disruption on the articular cartilage surface, in terms of severity, is up there with the most serious musculoskeletal injury that you can get. The likelihood of you returning successfully from a ligament repair is better than returning from cartilage repair. And so if you can rupture a ligament and save the cartilage, then that's the better way of doing it than rupturing or damaging the cartilage but saving the ligaments. And so to a certain extent, your analogy holds true, and that is that the ligaments, and to a certain extent the tendons as well, act as a fuse and therefore a safety mechanism to protect the musculoskeletal system, and in particular the joints. Make it easy. Good.
I don't know the optical success of this how the body makes these fibers, how everything is like muscle cells, we have cells, but tendons are somehow in between. So how they get
again, probably a question better targeted toward a kind of a bioscientist than me, but the tendon and muscle structures aren't hugely different, and so their growth is synthesized in probably a similar way. Obviously, tendons are predominantly collagenous, and so you could draw comparisons to articular cartilage. But it's probably targeted towards someone more knowledgeable in terms of the cell biology of the tissues than me.
the contact between the tendon and bone is kind of interlocked. So what is the contact between an implant and the tendon?
Okay. So let's have a think. So an implant in terms of a new knee or a new hip? Okay. So we don't get awful lot of contact between a new, let's draw that one there. So this is our knee, and if we talk about a replacement knee, then effectively the surgeon cuts off a slice of knee, not the whole lot, but a slice of knee, and fits in then a metallic replacement. Something not dissimilar to that. Now, one of the key questions in knee replacements is, do you keep the cruciate ligaments intact or not? The implants themselves don't have any contact with the tendons, because the tendons will actually, from the thigh muscles, for example, or the hamstrings, would actually insert on the other side of the joint. And so you have muscles up here, and then this will be a tendon. It runs down to insert somewhere down here. So the tendons actually bypass the joint itself, and that goes effectively round the back. It doesn't come around the side, it goes around the back. And you then have the patellar tendon that kind of comes from the front, from the muscles on the front of your leg. So we can discount the tendons at this stage because they don't have any role in the synovial joint themselves, but the ligaments are different. The ligaments and certainly the ones in the middle, the anterior and the posterior cruciate ligament, from an engineering design challenge, creates a problem. Because what we're kind of dealing with here is design for manufacture, in a kind of a strange way, insofar as when we, as engineers, manufacture these new designs, I'm not sure where my drawings go with this, but start again. So we effectively, if we look from the side, so that's the front, and that's the back. So that's kind of what a new knee looks like from the side. And so we as engineers can design them. We know the materials that we're allowed to use. We can use the correct materials. We can use FEA, finite element analysis, to make sure they're strong enough. We can ensure the surface roughness is good, i.e. that we can polish it. So there are a number of fairly elementary design stages that we can go through. One of the tasks that perhaps our undergraduates struggle with appreciating most is design for manufacture. And in this instance, we kind of deal with it in two stages. One of which is the pure manufacture of this. And we can get that right by talking to the workshop, by talking to the shop floor. But then this isn't the final assembly. This is only a component that has to be put into here. And that's the final assembly that, in this instance, takes place in a whole different world. If you're working for an engine company in a mechanical environment, this would be one component. And somewhere else on the shop floor, you would have a different setup. Maybe you worked in station A. Station B would then take your engine component, and they would assemble it all together. And so your engineering knowledge would be in line with the other engineers somewhere else on the shop floor, and you can make sure that the final assembly was designed appropriately, i.e. that you would be designing for final assembly and manufacture. Here, however, yes, we can manufacture it, but when it comes to assembly, we're talking about a totally different environment. We're talking about liaising with orthopedic surgeons who are in a clinical operating theatre, and they have to make this work under very different constraints to what people in an engine assembly plant would work in. And so one of the key questions is, how can you do a knee operation and retain the cruciate ligaments. We know they have great value because they stabilize the knee in tandem with those two on the outside. So these two aren't an issue. They remain intact. The anterior, the lateral and medial collateral ligaments stay intact. It's just the anterior and posterior cruciate ligaments are the ones that cause the design challenge because, in essence, they get in the way. So there are some implants that look at sacrificing those ligaments, so they take at least one out, and then they put their implant in. And now the question then is, whilst that might make for a beneficial engineering design, does the removal of one of these ligaments, does a sacrificing ligament design have negative longer-term impacts? And that's where the field again becomes very complex, because we can take our engineering design and we can put it in a machine and we can run wear tests on a new knee or a new hip, and they can run for 1 million cycles, and you can weigh the difference between your components at the start and the finish. And so you can get some idea as to whether they are good functionally or not. But that is only limited in terms of value. You can't accurately replicate the gait of somebody and the consequence of somebody walking differently because their knee doesn't feel quite as stable as what it was. And so this links back to our very first presentation, where we look at motion analysis. And so one of the numerous studies that's happening at the minute, no doubt, and there'll be hundreds going on around the world simultaneously, I suspect, are motion analysis groups trying to identify difference in performance between one type of design, maybe one that removes one of these cruciate ligaments, and other designs that retain the two of them intact. Because to wait 15, 20 years to see the long-term prognosis is difficult. But equally, to try and get any clinical data from somebody 2, 3, 4 weeks post-operatively is quite challenging as well, because different people respond differently. So by us having the ability to place markers on different landmarks, and then effectively creating stick people is of great value, because we can then start measuring angles between joints and measuring across a population that's sufficiently large to get some useful and valuable scientific data. So in terms of how do ligaments interface with implants, as such they don't, but they can't be excluded when it comes to designing them from an engineering perspective. Anything else? Okay, I suggest we have a 5-minute break, unless that was going to be a question. A 5-minute break, and then we'll continue with muscles.